specific heat capacity is how much energy is required, in specifically how much heat is required to change the temperature of an object by a certain amount. So how much heat is required to change an object's temperature. And remember, temperature is basically a measure of its internal energy. By a set amount. Usually that set amount is 1 degree Celsius per gram of object. So specific heat tells you how much heat is required to do that. It's also a way of measuring how much heat and how much energy an object can store. So objects with large specific heats will store large amounts of energy because it takes way more energy to change their temperature than other objects do. All right, so if you put toast in a toaster and heat it up to 350 degrees Fahrenheit, and do the same with the bowl of soup, heat it up to 350, not put it in a toaster. That was apparently very difficult for third period. At that temperature, so 350 degrees, soup burns you, but toast does not. Why? They're the same temperature. Got 350 degree toast, about 350 degree soup. We eat one, and it makes our mouth burn, and we eat the other one, and it's fine. So what's the difference? Let's assume it's the same, like, mass of stuff. Let's assume it's the same amount. You're right on the water. We're getting there. The water matters. The fact that soup is mostly liquid and mostly water. That does matter. Right. And why does water matter? If you're in this, if you're thinking microwaves. You're thinking microwaves. Doesn't have to be a microwave.
Okay, well, now I see why third period was confused. You're explaining this weird.
Yes, it's always my fault. Okay? You heat up soup, you heat up toast. They're both 350 degrees. The water matters, but not from that standpoint. What do you think? It's the heat capacity. So water has a higher heat capacity. That means with them both being 350 degrees Fahrenheit, the amount of energy in the water of the soup and the amount of energy in the toast are not the same because they have different specific heats. So soup has a higher specific heat. I'm going to call SH for specific heat. Okay? Specific heat capacity. There we go. Has a higher specific heat capacity. So, therefore, I'll say the water, too, for the soup, because that was a good thing. Soup has a higher specific heat capacity, so therefore, it has more energy to transfer. So, heat than toast. Okay? The toast is the same temperature, but not all temperatures are created equal. Okay? There's something else we'll talk about, which is conduction versus insulation. Toast is an insulator, so not only does it not gain that much heat, but it also doesn't transfer that heat very easily. Soup heats up with a lot of energy, and it transfers that energy pretty easily, which makes it really, really, really hot compared to toast, even though they're both the same temperature. So just because things are the same temperature doesn't mean they feel the same way. Okay? And that has to do with how they transfer heat and how they store heat. You can have some objects that transfer heat really well, but don't store a lot of heat or do store a lot of heat. Iron stores a lot of heat and aluminum does not. So if you have aluminum and iron and they're sitting out, one's going to transfer the heat, a lot more heat, but they'll both transfer the heat quickly. Some objects have a lot of heat but don't transfer it really quickly, like dirt. Like dirt has a lot of heat, but it doesn't transfer that heat really quickly. Whereas other objects may not have a lot of heat, but they transfer it really quickly to you, so they cool off really fast, even though there's not a lot of heat to them. Good. All right. Why is water so good at cooling hot objects? Caden, what do you say on this one? 14. So why would it absorb? Huh?
It has the higher capacity.
Yeah. So water has a high specific heat capacity. So it removes lots of heat quickly. Okay, an example. You have a wood branch on fire that you would like to put out. So you have two options. You have next to you a bucket of water, and on the other side of you a bucket of leaves. So you stick the thing in the bucket of water, and your friend sticks it in the bucket of leaves. Both of them should do the same thing. They should both absorb the heat from the fire, which would remove the heat of the fire, which would put the fire out. Okay? Water has a really high specific heat capacity, therefore it absorbs a large amount of heat from the fire really quickly, and that puts it out. Leaves, on the other hand, have very low specific heat capacity, so they don't absorb enough heat from the fire, which means the fire doesn't go out, which sets leaves on fire, and then, your house, all that stuff. Huh? Ooh, there you go. Make s'mores while the world burns around us.
Oh, okay. That got better.
Always. Okay? So water has a really high specific heat capacity. It's why we use water for so many things. Water absorbs lots and lots and lots of heat. Okay. Thermal expansion. Caleb, what can you tell me about thermal expansion?
I just wrote that it's the expansion and contraction of things due to heat.
Yeah. So as objects gain or lose heat, they expand or contract respectively. That just means that if they gain heat, they expand, and if they lose heat, they contract. But here's the big question. Why? Why do they do that? Like, that is what they do. But why do they do that? Because what? Right. We said that temperature is essentially a measure of an object's kinetic energy. So if the temperature goes up, the particles move faster, and that's going to cause them to spread out from each other. If they contract, if they get colder, it'll cause them to contract because they'll move slower than each other. Okay, so they expand or contract respectively. Faster moving particles spread out. And vice versa. Let's look at a good example of this real quick. So you got your practice 1 sheet. On the back, I believe we did 12 already, right? Where we talked about temperature of space. Look at 11. So one way to open a jar that you cannot open on your own is to run it under hot water. This actually works. Why? More so the lid, but yes, we get an expansion. Now the air in the inside would expand more the jar itself, but the lid, usually the lids are made of metal. Like a lot of these jars, like pickle jars and stuff like that, a lot of the lids are made of metal. So if you heat it up, it'll cause the lid to expand, which should make it a little easier to go. So increasing the temp of the lid should cause it to expand. And this is all over the place. I'm going to show you a demo of this next time. But another example, you ever been on like really long bridges, especially over water, that have like these teeth in them? They got like these little gaps with like forked teeth in them. That's because in the summer, the bridge expands and those teeth go into each other. In the winter, it contracts and they go away from each other. So it allows the bridge to expand and contract. Otherwise, older bridges have like these bumps in it when they spread and then they rip apart. So that's why they have those. They build bridges in sections instead of one huge thing. Good. All right, let's look at this last question. Solid state of most materials sink when they're placed in liquid. However, water floats when the solid state, ice, is in the liquid state. So why is this? So most objects get denser when they get more solid. But the reason is water expands when it freezes. Okay, and here's why. Most objects, so like iron, when iron is a solid, it looks like this. All its particles are lined up, not perfectly, but relatively neatly in these kind of ordered little rows. Water is a little bit different than that. Water forms a crystal. So that means its particles are in more kind of shapes like this. Let's see how many have it done so far. Well, you can kind of see where I'm going with this. You can see that with the same number of water particles, I take up way more space. And that's because when the water particles freeze, when they lose energy, instead of them getting closer together, they actually spread out and get further apart. And that's because ice is less dense than what water is, and it's because it forms these kind of crystal structures. You've heard of ice crystals before. That's the real correct terminology for it. Ice does form a crystal structure. Which, again, it's a drop in the bucket of the weird things about water. There are so many things weird about water, and we'll talk about a lot of them. Water has a really high specific heat capacity. Water is less dense in the solid state than it is in the liquid state. There's so many things about water that are just bizarre, which makes sense why it's kind of the stuff of life, as you call it. Because nothing else does what it can do. All right, any questions on the notes page? All right, what I want you to do is I want you to jump to the practice sheet.